Hello, everyone. Today we are going to be moving on to our next target, which is all about applying exponential equations. So we just spent a day all about kind of graphing them. So we know that exponential problems, if it looks like an exponential growth problem, it always kind of like gets exponentially, it gets large, really fast. And if it's a decay type problem, it's going to look, wow, that's not really that great, but exponential decay gets really small really fast. And it's all based on kind of the rate that those things go. And the reason why exponential equations are so important is they actually do have a lot of real life applications. There's a lot of things in math that don't have the direct application that exponential function does. You guys have probably heard of like when you save money in a bank, eventually when you get to a certain point, that money will grow exponentially, which is why they always recommend saving as much as you can in the beginning because it'll pay off later in life. But it also applies to a lot of other situations. Money is a common one that has exponential growth. A lot of things in real life, like when you buy a car, um, it's kind of sad the value of it decreases as soon as you drive it off the lot. And every mile that you drive it, it decreases even more, which is, I know, is kind of sad, but it's how buying a vehicle works. Those scenarios, though, the fun part about it is those follow the exponential curve. So there's some general equations that we're going to work with today, and we're always going to give you guys the equation, but there's a lot of situations that we can apply those scenarios to, and they all kind of have their own formula that works, but all of them are exponential equations because the variable is always going to be actually in the exponent. So the first scenario that we're going to work with is obviously the first example. And this is actually kind of a classic scenario, not a real life one, obviously, but it says today there are 2,875 zombies in the state of Illinois. The zombie population has increased by 45% per day. In 15 days, there will be a news report about the current number of zombies. How many zombies will the news report say there are? So this formula right here, and you'll notice it's pretty similar to the one right below it. Only difference is that plus and minus. And that's because the plus right here, this stands for growth. That's like when you have an amount that's growing and getting larger. And the subtraction is when you're working with decay, which is like something is going to be getting smaller over time. And these variables, they mean the same thing in both of these. So A is what we always call the initial amount. Kind of like however much we're starting of whatever it is we're measuring. So in this problem, when we're finding A, whatever the problem is about, we're talking about the number of zombies. So the initial amount of zombies is 2,875. That would be our initial amount. Now, when we talk about R is what we call kind of the rate. It's either the growth rate or the decay rate, depends on the problem. In this case, because we're adding and because the zombies are multiplying, the growth rate is always going to be kind of given to you on this. It says it's 45%. Now, it is 45%, but the key with the rate, when you plug it into the formula, it has to be written in decimal form. So I'm not going to rate it as 45%. We're going to take that decimal place, we're going to move it twice, and 0.45 is going to be the rate that we're working with in this problem. And the last variable, we did define A, we defined R. T, you probably might be able to guess, but this represents kind of the time it is that you're taking here, which could be in days, weeks, months. It all depends on kind of what the growth rate is based on. So here it's 45% per day. So as long as you're working with days, that's the unit of time that T is going to be in. Okay. So in ours, we're working with, we want to know how many zombies there are going to be in 15 days. So really, when I take all my information, it's just going to be a matter of really plugging it all in. We know my initial amount is 2,875. We know that the growth rate is going to be 0.45, plug that in. And t, I'm raising it to the 15th power. So if it helps, I always kind of try and simplify what's inside first, just to make kind of the simplifying in two steps in case you mess up. But if I take 1 plus 45, 1 plus 0.45 raised to the 15th power, that's going to turn out to be 263, approximately 0.34, which if we multiply it together, that means, whoo, that was fun. Y is going to be approximately 757,102.5, which, remember, we're talking about zombies. So our final answers are always going to have units, but you can't have 0.5 of a zombie. So 757,000 and approximately 103 zombies, which is pretty terrifying if you ask me. That's like a Walking Dead scenario, but that would be your amount. So exponential equations have a lot of cool different types of kind of problems. But again, they all might have some different formulas. Like we're going to look at example 3. This one has a slightly different one, but again, the variable is in the exponent. That's what makes this an exponential equation. Now, this particular scenario, if it's this, when you're working with a problem that looks like this, A and B, A is really always going to represent kind of the same as above. It's the initial amount. B is still going to represent the rate. But kind of like before, that rate sometimes is something we might solve for that. So for this problem, it says, okay, you are studying microbiology. At the beginning of the day, you see that there are 3,700 bacteria cells in the culture. 4 hours later, you estimate there are 34,000 bacterial cells. Write an exponential equation to represent the bacteria growth. Now, when you write that equation, you have to know whatever the growth rate is. So for something here, I noticed that they don't actually tell me that. They tell me that obviously at the beginning, there's 3,700. So I know for a fact, I know that there are 3,700 bacteria cells in the culture. And it tells me that 4 hours later, T, it tells me my time, which is exactly what X stands for. The exponent in most exponential equations usually represents time. So part of my equation, what I know right now, I know that it's going to be 3,700. I don't know my growth rate in this case because it doesn't tell me. But I do know that here that it tells me after 4 hours, there's about 34,000 bacterial cells. So the cool part about that is that really here, that is really just an ordered pair. Technically, my equation is everything here, but you have to figure out what B is. The rate is always something you need to know before answering really any questions about this. So honestly, that kind of has to be our first step. I'm going to plug in 34,000. This is going to be my Y. This is going to be my X. Plug in. My time is 4. And all we have to do now is simplify. And we just did a whole unit on this. To get my variable alone, I'm going to divide by what's in front. Now, that's not the nicest number. That turns out to be about 9.189-ish b to the 4th. And our last step is going to be, we're going to take the 4th root of this. Now, because we're dealing with a real world scenario, technically even roots, remember, those produce plus or minus answers typically. But because we're in the real world, we don't really care about the negative answer here. We only care about what it turns out to be, which is approximately 1.74. That is our growth rate, which is absolutely insane. That's an 174% increase, which is insane every hour. But the important part is that you now know your full equation. You know it's not B anymore. We know that our growth rate is about 1.74, and we can leave the time. And now we can actually answer the question. It says approximately how many bacteria are there in 6 hours. So all we have to do, wow, that went crazy, is take 6, plug it in, And we get our final answer of approximately 102,682 points, approximately 6 to 8 bacteria. Okay. If you wanted to round that up, you could, I guess. I don't know. Bacteria, do those come in parts? Probably not. It's an unformed one. All right. Now, in terms of all the applications, there's kind of two different types that we are going to work with here. And these are more money related than anything else. So one of the different scenarios that we work with is called compound interest. And the other one is really similar. It's continual compound interest. And both of these really have kind of a similar formula here. So compound interest, what exactly this is it's a way of how we can calculate something's worth over time. And the formula is A equals P, and then in parentheses, 1 plus R over N, all being raised to the NT. Okay. Now, continual compound interest, you'll see that it's going to look kind of similar. The formula for this is A equals P E to the RT, which I will explain in just a moment. But these two formulas are really how we calculate kind of how money follows an exponential curve. And this is more like if you're saving something. So if you look at the first example, it says you deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 2 years if the interest is compounded quarterly. So this is kind of assuming, for example, you have this money, you're going to invest it in this account, and how much money is going to be in there if you don't touch that $4,000? So in this formula, all these different variables, they represent obviously some different things. So really this just represents the amount at a certain point in time. Oh, that didn't work at all. Certain point in time. Usually, for example, that's like what you're trying to find. You're trying to say, I have this amount. How much is it going to be worth 10 years down the line? P is what we call the principal, which is really just the initial amount. Kind of like how much are you starting with? So like, for example, in our problem here, our principal is going to be 4,000. That's how much we're starting off with. That's how much we're starting off putting in the account. So that is our principal balance. Now, N, this stands for the number of times per year that something is compounded. So that's what we actually mean when we say compound interest. It's kind of like how many times are we going to be applying this interest? So for example, there's a lot of common words like annual. Annual means once per year. There's a lot of different words actually, but like semi-annually is twice per year. Quarterly is 4 times per year. So there's a lot of common ones. These are probably some of the most common that we use, but that's what we mean when we say number of times per year. So like this first one, it says you deposit $4,000 in an account, find the balance after 2 years if the interest is compounded quarterly. So what this means, this tells me what my end value is. If it's compounded quarterly, we're compounding this 4 times per year. If you look at example 5, it says it's compounded daily. Well, how many days are there in a year? There's 365. So the end value on this one would be 365. Now, the other two pieces, these are the same as the last formula. T always represents the time. It's how much time is passing that you want to see how much is going to be in there. And obviously R stands for the rate, which we're still going to write as a decimal. Okay. So for all of those pieces, we are going to find everything else. Our R in this case, we know our rate. It says it's 2.92%. So as a decimal, that's 0.0292. And obviously, we're looking at our time. We're saying we want to know what's happening after 2 years. So 2 is going to be our amount. So all we really have to do is go ahead and we're going to plug this all in. Wow. Okay. So my amount here, we don't know A, that's what we're trying to find. But I know my principal is 4,000, so P comes first. In parentheses, it's 1 plus whatever your rate is. Your rate divided by N. So that's because it's divided up over however many times it's compounded. So it's going to be 0.0292 divided by N, which is 4. And I'm going to raise it to it's N times T, which is 2. And to be honest, we're really just going to type this into our calculator exactly as it looks. If you want to start by typing kind of what's inside, I kind of sometimes work my way through. Start by typing in what's inside. We are going to get A equals, wow, pen is not working today, guys. Sorry. A is going to be equal 4,000 times, that all inside turns out to be 1.0073. And then 4 times 2 is 8. And now this is something that's a little more manageable to type in. If we type all that in, we are going to end up getting 4,239 and 60 cents. All right. So that's how much is going to be in there. Now, that's pretty much how you do all these problems. The only difference is if you guys go to where it says applications of continual compound interest, all of these variables stay the same. The only difference is this variable in here that you see, which is E. Now, E works actually kind of similarly to pi. It's kind of like pi is a symbol, but it stands for a number. That's exactly what E is. E is called Euler's number. And it ends up being like 2.73 with a whole bunch of other repeating random decimal places, kind of like pi. But for us, for our purposes, this is just going to be on the calc. Why didn't that work? Not cola. It's on the calc. So the buttons to find it on the calc, we start by hitting the second key, and then we're going to press, it's right above the divide key, actually. If you go to the calculator, it's in blue, you'll see right above the divide key. So if I hit the second key and then I hit divide, E is going to pop up. If you just click enter, you're going to see, 2.71. I think I said 2.73, but it's 2.7182818285, and that decimal goes on forever. So instead of doing that, E, that is just what we're going to use in place of E. And that's E. When it says compounded continuously, it literally means it's compounded every second of every day, which that's why we have to have kind of a way to approximate this. But all of the other variables end up staying the same. And that really is exponential equations. There's other types of problems out there, but we're really going to stick with more of like the real life situations, like bacteria cultures, or there's some like compounds out there that actually decay. Like you probably talked about radioactive decay in in maybe your science classes, but that's actually exponential decay. It follows that formula that we're talking about. So if you guys don't have any questions, if you want to try some of the You Try Nows at the bottom, you can. If not, though, you can get a start on working on the homework for today.